Okay, 7.2 is about finding eigenvalues of a matrix. 7.3 is going to be about finding the eigenvectors. So, I apologize in advance for any coughing and sniffles. Let A be an n by n matrix. Remember, we've defined a non-zero vector v satisfying an equation AV equals lambda v for some scalar lambda to be an eigenvector for the matrix A with associated eigenvalue lambda. Okay. So suppose we've done our little characteristic polynomial thing from the last section. We've found some eigenvalue lambda of A. Then we can define the lambda eigenspace E sub lambda to consist of all the lambda eigenvectors of A, right, all the eigenvectors with associated eigenvalue lambda, together with the zero vector. Remember, we haven't allowed the zero vector to count as an eigenvector, but we are going to throw it back in to define the eigenspaces. Okay, and one reason why is because then we have this nice expression for the lambda eigenspace. And so let's explain why this holds. Basically, E lambda we could write as the set of all vectors v in Rn such that AV equals lambda v, right? The lambda eigenvectors are all such vectors, all solutions v to this equation except for the zero vector, and then we're throwing in the zero vector too, so we in fact get all the solutions. And just as we did for eigenvalues, we can rewrite that equation by bringing the lambda v over to the left and putting the identity matrix in, and then factoring out the v, we get A minus lambda times the identity matrix times v equals a zero vector. And that is just all the vectors which this sort of compound matrix maps to zero, right? So that's just the kernel of A minus lambda I, okay? Which is what I was claiming up here. So that is a nice formula for the lambda eigenspace. And, well, it's really nice that it's the kernel of something, right? Because we know that kernels are always subspaces. So here's a theorem. Every lambda eigenspace of an n by n matrix A is a subspace of Rn. Okay. We noticed this earlier when we were playing around with the pictures in Mathematica that, you know, if we had an eigenvector in some direction, then basically everything else in that direction was also an eigenvector with the same eigenvalue lambda, right? And the same thing would hold if you took linear combinations of a couple eigenvectors with the same eigenvalue. Then all the linear combinations would still be eigenvectors with the same eigenvalue. And so you get subspaces. These things are closed under scalar multiplication and addition. Okay, well, now that we have sort of this nice expression for E lambda, let's find it for this nice matrix here. First we got to find the eigenvalues. So remember from last time that we want to find the determinant of A minus lambda I. Excuse me, I3 in this case, I guess. And sometimes for determinant, people just put vertical bars on the matrix, and that means take the determinant of the matrix. So I'll use that notation, and we're just supposed to subtract lambda from the main diagonal entries, so we get 1 minus lambda 1, 1, and then 1 minus lambda 1, and 1, 1 minus lambda. Okay. And you can copy the first couple columns over here if you want. First of all, we get 1 minus lambda cubed, and then 1 times 1 times 1, and 1 times 1 times 1, so plus 1 and plus 1. And then we are subtracting 1 times 1 minus lambda times 1. And actually all three of those products are going to be 1 minus lambda, so I'm subtracting 1 minus lambda 3 times. Okay, that's my characteristic polynomial. And so if we expand out this cube, remember the excuse me, the third row of Pascal's triangle is 1, 3, 3, 1. So we got remember your minus sign here, negative lambda cubed plus 3 lambda squared minus 3 lambda plus 1, and plus a couple more ones. Then down here we have minus 3 and plus 3 lambda. Okay. And well, plus 3 minus 3 and minus 3 lambda plus 3 lambda, the only thing left is these first two terms. And we could factor out a lambda squared there. And if we do, what's left over is just 3 minus lambda. And so if we want to find the roots of this guy, then we are going to get lambda equals 0 or 3. Okay, so those are the two eigenvalues of this matrix. So we have to find E0 and E3. Let's look at E0 first. And for some reason, horizontal lines left to disappear when I do this. I don't know why. So by our result above, E0 should be kernel of A minus 0 times I, through IN, I3 in this case. That's just the kernel of A, right? So kernel of this nice matrix. Excuse me. And so let's just see. Let's see if we can just guess it by inspection here. So it's going to be the span of some basis for the kernel. And we just need to look for linear combinations of the columns that are equal to 0 vector, right? And I could take 1 times the first one, negative 1 times the second one, and 0 times the third one. Or something independent from that would be 0 times the first, and then 1, and then negative 1, right? Or I could have done 1, 0, negative 1, or something like that. But I don't want to add that third one here, because that would be a combination of the first two. Okay. So let's write those as column vectors, 1, negative 1, 0, and 0, 1, negative 1. Okay. And if you're not 100% convinced that there's only, sort of a two-dimensional kernel here, we'll remind ourselves on the next page why that's the case. Okay. All right, and then we have an eigenvalue 3 as well. And so let's find the 3 eigenspace. That's the kernel of A minus 3 times the identity. So we're going to take our matrix A and subtract 3 from the main diagonal entries. So we get negative 2's on the main diagonal. And can you see a linear combination of the columns that equals 0 this time? If you stare at it for a little while, you might realize that just the sum of the 3 columns is going to be 0, right? Negative 2 plus 1 will be 0, and so on. And so, 1, 1, 1 is certainly an eigenvector. And in fact, anything else in the kernel here is going to be a scalar multiple of that vector. Okay, so that is a basis for this kernel, and therefore the basis for E3. Okay, so there we have it. Now, what do you think? Is this a diagonalizable matrix then? It's not diagonal, right? It has non-zero stuff off the diagonal, but diagonalizable. We know that happens if and only if it has an eigenbasis. And well, here we have 3 nice independent eigenvectors. Okay, and 3 independent vectors in R3 form a basis of R3. Okay, so we do have an eigenbasis, and excuse me. Therefore, A is diagonalizable. Now, if you don't like this sort of guess and check inspection method, remember the other way to find the kernel. You're just solving the system, A times X equals a 0 vector. So you can just do Gauss-Jordan elimination on this matrix. I tried that and I got 1, 0, negative 1, and 0, 1, negative 1, and 0, 0, 0. Okay, so well, you could look for linear combinations that give you the 0 vector, and maybe now it's even easier to see that 1, 1, 1 will do the trick, so you get the same vector. Or if you want to go back to chapter 1 stuff, then you can just, write the system out again. Right, this is what's been lurking here while you did your elimination. And you just get a couple equations back out of that. X minus z equals 0, and y minus z equals 0. So x is equals z, y equals z. All three variables have to be equal. So your general solution, excuse me. Well, I'm supposed to set them equal to a parameter, aren't I? Let me fix that. I was going to call it xxx, but I should probably instead, set z equal to parameter t, and then x and y are also t, so you get t as your general solution, and that is t times the vector 1, 1, 1, right? So 1, 1, 1 is the basis for the kernel. All right, well, let me go get a drink, and then we will start a new video for page 2.